All right, class, welcome back. Here we are, lecture 23, and we're going to spend today fleshing out the ideas of the renormalization group theory. This is where we ended off last lecture, having built up some intuition that critical points are special in that they are scale invariant. If I take a system and I put it at its critical point, and then view that system at a variety of different scales, zooming in or out, the system looks the same. This is because the defining feature of a system at its critical point is the divergence of the correlation length, which means that a system at its critical point has fluctuations that exist on all scales. And because, therefore, there is no characteristic scale, save the size of the system, viewed on different lengths, the system looks the same, at least to the extent that you're already far enough out that you don't notice the kind of fundamental length scale set by the size of the unit cell or the atoms that make up the system. This was kind of a saving grace, a last-ditch effort to try to understand universality and critical exponents, since we had gone through a number of different approximate means to tackle the Ising model and really failed to make a lot of progress, at least in the 2- and 3-dimensional systems, which are easily probable experimentally. So after a quick review, going over those different means that we've used to tackle approximately the Ising model, I'll introduce you to the renormalization group as first worked out by Kandanoff, the so-called block decimation scheme for the Ising model. We'll do this in 1 dimension and then 2 dimensions and see that actually we get some pretty good results. They're still not quantitatively accurate, but there are subsequent bells and whistles that you can put onto the basic approach that I'll outline here that brings you to quantitative accuracy in a way that our other attempts to formulate approximations or approximate solutions to the Ising model have failed to do. Okay, that being said, let's go ahead and review. Let's talk about where we've been. So we have, over the past couple weeks now, considered a number of different approximate solutions to the Ising model. Of course, the whole reason why we have to develop approximations to the Ising model is because as an interacting model, it doesn't conform to those simple tricks we've used in non-interacting systems to compute the partition function, the object we'd really like to be able to have our hands on so that we can get observable properties from. So we started down this path by employing something called mean field theory. That's where we took our big interacting lattice and got rid of everything but one tagged spin and replaced that fluctuating environment in which that spin was embedded and replaced it by just some average field. We then, having found that mean field theory was, while sufficient to predict spontaneous symmetry breaking, insufficient in that it didn't differentiate the behaviors at different dimensions. And we formulated a first try to fix it using thermodynamic perturbation theory. That was where we formalized first our mean field theory a little more rigorously, expressing the interacting energy of the Ising model into a sum of 2 pieces, a mean field piece, a piece that would serve as a reference, and then a correction. Thermodynamic perturbation theory then takes that correction and tries to handle it perturbatively, which generates expectation values taken in the reference, in this case a mean field reference, And unfortunately, we found that because fluctuations diverge in the way that they do in lower dimensions, thermodynamic perturbation theory was never going to bring us quantitative accuracy in 3 dimensions. However, it does in 4 dimensions and higher. Again, owing to how quickly mean quantities increase relative to fluctuation quantities in high dimensional systems. Our final attempt using kind of traditional physics methods to treat interacting systems was to formalize a variational theory. This was utilizing the properties of convexity associated with exponential functions and saying that maybe we can try to find an optimal reference with which to compute quantities. We illustrated that by trying to find an optimal single spin system, non-interacting spin system, to map the Ising model onto, and found that, in fact, the optimal one parameter theory for the Ising model is the mean field theory we had written down initially. All of these essentially led to the same self-consistent equation that m is equal to hyperbolic tangent of beta jz m plus beta h, which we can solve to predict critical exponents and spontaneous symmetry breaking. And consequently, as they all led to this same relationship, they all subsequently give the same result. Now, it should be said that these different means of tackling interacting systems they have their place. There are questions for which mean field theory or perturbation theory or variational theory works exceedingly well. We will use thermodynamic perturbation theory in a couple weeks to derive the van der Waals equation of state, treating an appropriate reference system close to that of an ideal gas and perturbatively correcting for interactions. That works very well, gives us the van der Waals equation of state, which of course has great utility. Mean field theory, you all have some sense of, probably in the context of quantum mechanics, as essentially describing chemistry. Nearly all of chemistry that you learn in your introductory courses is built upon a mean field theory, so of course that has utility. Variational theories work quite well often. Often mean field theories can be put in variational forms, as we've seen them in this context. One of my favorite examples of a variational theory for a complicated interacting problem is the problem of an excess electron in a lattice, so-called polaron problem. Feynman used the variational theory to essentially solve it. So they all have utilities, which is why I spend the time to kind of introduce them, even though a critical point, a system at its critical point, is not one of those which are so conducive to these sorts of standard techniques. All right, so essentially from each of those approximations, we learn that they all break down if we get close enough to TC. And they all have the same reason, which is due to the fact that we have a divergence of the correlation. length. Critical points are really singular in their difficulty in studying. So we ended last lecture having gone through variational theory, having noted this kind of fundamental physical insight that potentially gives a critical point some simplicity, which was that maybe if we try to take that system exactly at Tc, and when we actually took a system at Tc, we noted that a simplifying feature of that system was that it was scale invariant. That realization has then led us to what is the focus of today's lecture, the renormalization group. Or what the cool kids call RG. It was the subject of the Nobel Prize for Wilson in 1982. The essential insight of the renormalization group is that due to scale invariance, if I change the scale of the system, I get the system back. That is very different from what happens normally away from the critical point. If I change the scale, it usually is like changing the effective strength of interactions or the effective temperature. What we mean by that a little more quantitatively is that if we were to note the correlation length of the system as a function of temperature, at Tc it's infinity, but as we lower the temperature, the correlation length decreases. Or on the other side, if we increase the temperature, the correlation length decreases. Decreasing correlation length is like zooming out of the system, viewing it on a larger scale. Now, we've had a big to-do about this mean scale invariant at the critical point. It's also worth noting that if I was at 0 temperature, the system would be scale invariant also. If I was at 0 temperature, the system would be a perfect all spin up or all spin down. If all of the spins are up, I don't know if I'm viewing it on a large scale or a small scale, it would just be all black or all white. Similarly, the system is scale invariant at infinite temperature. At infinite temperature, the correlation length reduces to just a single lattice site. Spins are independent of each other. So I will see on average just one big gray blurb. Whether or not I zoom in or out, I just see continually that gray independent field. But those are cases where it's trivial. We expect the system to be scale invariant. It's unexpected for the system to have a finite temperature scale invariance point. Just to make clear what I mean by zooming out and changing temperatures, let's consider the Ising model at a couple different temperatures and actually think about what it would mean to change the scale. All right, let's choose this middle box to represent our TC. We know at TC, the system is complicated. There are fluctuations that exist on all scales. So we have big clusters of spin up and spin down, small clusters of spin up and spin downs, and everything in between. We know at very low temperature, some T1 less than T2, where T2 is some temperature less than Tc, that if we're at very low temperature, if everything is predominantly spin down, as long as the temperature is finite, there will be little islands of spin up. They will have some characteristic size set by that correlation length. If I increase the temperature, that characteristic size will grow. The fact that that characteristic size grows is then synonymous with, if I was to take the system at the lower temperature, zoom in, that little region, little island of spin up and a predominantly spin down background would look like it was at effectively a higher temperature. On the other side, if I took a system at high temperature, call it some T4 greater than T3, where T3 is greater than Tc. Well, at really high temperature, system is up and down in equal proportions, but there is some still favorable interaction energy to have like spins near you. If I decrease that temperature, that tendency will increase, growing those domains. Again, just to emphasize that the system is up and down in equal proportion above the critical point, unlike what I expect to see below the critical point. And if I take that system at T4 and I zoom in, well, the system is still up and down in equal proportions, so it will look gray on average. However, those little domains that clump together some amount of spins up or some amounts of spins down will grow. In fact, they will grow in such a way that there is a temperature that is higher that it would look like. This is to be contrasted with what I would see if I took the system at the critical point zoomed in or out, I would find that the system looks the same. Okay, so that's the picture we should have in mind, that we are going to take this bit of physical insight that there are points of scale invariance, T0, infinity, and Tc, from which, if we look at this system on different scales, the system looks invariant, looks the same, and try to formulate that basic idea now mathematically. So we need to understand what it means like to zoom in and out, and what it would mean like for the system to be left scale invariant. Okay, so we sketched this a little bit right at the end of the last lecture, and let's talk about it. How to implement this idea in math. Okay, so we're going to warm up by considering the Ising model in one dimension with no applied field. Now, you should all be, reaching back in your memory and reminding yourself of Landau's argument for the one-dimensional Ising model that says it does not have a phase transition. So we are likely to learn something in doing this, but we should not, for example, find a critical point by doing this. If we did, we would have found the same problem as we had in our mean field theory, namely the prediction of a critical point that does not exist. All right, but spoiler alert, RG will not predict a critical point for a one-dimensional system, so it's worth going through this. All right, so let's see. So we've got a one-dimensional Ising model. What does that mean? It means we have spins that sit on the line, could be up or down. Let's call this one spin 1, that one spin 2. We have a 3 and a 4, a 5. Let's do one more, and a 6. All right. So there is some intrinsic length scale between those spins. Call it L, the lattice constant. And we know that these spins interact. There's some exchange coupling, even in one dimension, that will bias neighboring spins to point in the same direction. We're going to call that K as the coupling, which is J in units of the thermal energy beta. Now, the idea behind scaling out is to take this system and try to view it on a larger scale, and doing so by integrating out half of the spins. So I'll choose to integrate out the even spins. So if I could work out that operation, I would be left with a system that it now looks like the Ising model. Again, I have spins on a line, but now they are a little bit further apart. Now they're twice the lattice constant apart. I might expect that spins on a slightly different scale interact with not the same coupling, but some different coupling. Call it K prime. Indeed, if the physics of this is just the bare exchange coupling, you would expect that, think it's intuitive that if I move the spins away from each other, that coupling is weaker. The operation that we're going to do, however, is not just to physically move them away from each other, but to really take this integrating out seriously, which is to note that in the original model, the model up here, with the lattice with all of the spins, the energy function that we've written down a number of times has one interacting with two, but not directly with three. However, because one interacts with two and two interacts with three, there is a correlation between 1 and 3. You can think of that as an interaction mediated by spin 2. By 1 interacting with 2 and 3 interacting with 2, 1 and 3 in effect interact. That is really the origin of what the new coupling K prime will be. If I average over all the possible ways that spin 2 can be, having done that, what is the effect left between 1 and 3? So we can understand this by writing down the partition function for this one-dimensional spin chain. Call it Q for the canonical ensemble we're considering, in which case I have a sum over spin 1, a sum over spin 3, all the even spins, and I can group those sums separately from the odd spins. But of course, the Boltzmann factor is there for all. Again, just being concrete, what we mean by this K is beta J. And again, in a one-dimensional system, I can write down those interactions between neighboring spins as a sum over I and I plus 1. So the name of the game will be to try to actually do that sum over the even spins. Get a partition function back that still requires us to sum over the odd spins. But what we will be summing over is some function that we will call e to the minus beta some a tilde that is a function of just the odd spins. And the question is, can we write that remaining function, e to the minus beta a, some function of the odd spins, in the form that looks like the original Ising model we had? Namely, can we write e to the minus beta a of spin 1, 3, 5, etc. as something proportional to e to the k prime, some new effective coupling constant, a sum of S1 times S3 plus S3 times S5, all pairs of odd spins, namely an Ising model with a new effective interaction. So this is then how we would implement zooming out, changing the scale of the system, and asking, does the system look like it's at a different temperature? If the temperature increases, that k prime would be smaller than k. If it decreases, that k prime would be larger than k. The system would be more strongly coupled. If it is left invariant, we would have found a critical point. All right, so what do you all think? Do you think we can write it in this form? Well, let's try to do it explicitly for a couple pairs of spins. Say, let's consider all the contributions so that a function due to summing over S2, one of the even spins. So that term, sum over S2, e to the k, S1, S2, plus S2, S3. Those are all of the terms in the partition function sum that have to do with S2. Now S2 as a spin can be plus or minus 1. This is a sum we can do. It's not so hard. We've done this sum a bunch of times. We get twice hyperbolic cosine k times the quantity S1 plus S3. I get one exponential with a positive sign in its argument for S2 being plus 1. I get one exponential with a minus sign in its argument from S2 being minus 1. The sum of those two exponentials with opposite signs in their arguments is related to the hyperbolic cosine up to a factor of 2. Now the question is, can we write this as some exponential of a k prime S1 times S3? At least, can we do so up to some constant independent of the microstate of the system? That constant, let's denote f of k. It could be dependent on k. In fact, there's clearly going to be a functional dependence on k. It's there in the explicit sum. But can we re-express twice the hyperbolic cosine as this form here, f times some exponential? Looks like an Ising model at a different temperature. Well, let's see. So we have essentially two unknowns, f of k and k prime. We're going to need two equations. So let's think about making a table. What are the possible values that S1 and S3 could take? What is the consequence for twice hyperbolic cosine k S1 plus S3? How would that relate to f of k? or e to the k prime S1 times S3. That's a terrible table. Let's try all that again. All right. Well, S1 could be 1, S3 could be 1. If that was the case, we would get a twice hyperbolic cosine k, 1 plus 1, that's twice hyperbolic cosine of 2k. F of k is independent of the spin, so it's still f of k. And if we multiply S1 times S3, we would get e to the k prime. What's another possibility? So that gives us one relationship, that this factor, twice hyperbolic cosine, is equal to f of k times e to the k prime. What if they're opposite? What if S1 is 1 and S3 is minus 1? Then essentially we'll have enumerated all the possibilities. Those are the two unique ones. They're the same or they're opposite. If they're opposite, that means we have cosine, hyperbolic cosine of 0. That's 1 times 2 is 2. F of k again is independent of the spins. E to the minus k prime is what we get when we multiply S1 and S3 when they're not the same. So now look at this. We've just stumbled upon two equations for the two different possible scenarios for S1 and S3, two unknowns. We can solve them. Doing so, we find that f of k is equal to twice the square root of hyperbolic cosine of 2k, and e to the 2k prime is equal to hyperbolic cosine of 2k. We have a relationship, a complicated one, mind you, but a relationship nevertheless between k prime and k. We would call this k being renormalized. By integrating out half of the spins, we find a k prime, which is now different from the k that we started with. In fact, we could do this now for all of the spins. Every even spin is going to act in the same way as our S2 just did. Which means that we will get a partition function for the original k and the original number of spins that is now equal to n over 2 factors of f of k times a partition function with a new coupling constant k prime that is of half of the spins we started with. There's now a relationship between the original partition function with n spins and the new partition function with half the spins and a new effective coupling constant. So we have not solved the partition function, but now we have a relationship between them that we could imagine iterating. This is a recursion relation. We could continue doing this again and again and again to actually solve the partition function should we want. However, it's sufficient to note that since e to the 2k prime is equal to 1/2 e to the 2k plus e to the minus 2k, that's hyperbolic cosine of 2k, that is necessarily less than or equal to e to the 2k, since we started with a k that was positive. So by iterating, by integrating out half of the spins, what we have done is generated a new Ising model with a coupling, with a strength of interactions that is less than the coupling we started with, or with a temperature which looks effectively higher than the temperature we started at. What that means is that when we take a one-dimensional Ising model, when we zoom out, we look at the system on a larger scale, it makes the system look like it's at a hotter temperature, necessarily so. So what does that actually mean? Physically, that means that if I look at the system on larger scales, the one-dimensional Ising model, looking hotter means it looks less strongly interacting, means there's more disorder. In fact, we knew that that was true. The one-dimensional Ising model at any finite temperature does not have spontaneous symmetry breaking. If I look at large enough scales, I have to find equal amounts of up and down. We could actually imagine iterating this flow say by starting at a system at low temperature. If we looked at the system on a larger scale, the system would look like it's hotter. If we did it again, it would look like it was even hotter, and it would keep doing that, looking more and more disordered. However, if k was infinity, or therefore temperature was 0, if I put infinity into this relationship, e to the infinity is equal to e to the infinity, which is also infinity. So I would get a k prime, which was infinity. That's a fixed point. If I'm at 0 temperature and I zoom out, it doesn't look different. Also, if k was equal to 0, that's e to the 0 plus e to the 0, that's 2 over 2 is 1. I get e to the, if I put in 0 there, e to the 0 is 1, and 1 is equal to 1. It didn't change. So if the temperature is 1, or is 0, or infinity, which is how I could get k to be 0, the system doesn't change. I have just found the two trivial fixed points of a system without a critical point. Those aren't exciting fixed points, but those are fixed points. If we iterate this map, look at larger scales, only if we start at 0 temperature or infinite temperature will the system continue to look the same. All right, that's the warm-up. Now let's see, how do we apply this to a two-dimensional Ising model where we expect to learn something interesting. So first, before we do the calculation, what do we expect? Well, if I was going to iterate this flow in temperature, if I was at a temperature close to infinite temperature, I expect that if I zoomed out, it will look hotter. If I'm below TC, I expect that if I take the system I looked on larger scales, the fact that the correlation length is finite means that it will look more ordered, so it would look more like it does at 0 temperature. So I would flow away from the critical point and have 3 fixed points that if I start at infinity, 0, or TC, the system would be left unchanged. But note the direction. There are 2 directions of the flow when there's a finite temperature critical point. Above the critical point, looking on larger scales makes the system look more disordered. So it flows to the infinite temperature fixed point. Below TC, zooming out, looking on larger scales, makes the system look more ordered because those fluctuations that break local order are finite in size. So if I look on larger scales than them, I will start seeing them disappear. Okay, so let's consider this calculation in 2D on a square lattice. All right, so let's put some spins down on a square lattice. Okay, there's our lattice. Let's denote this spin 1, spin 2, spin 3. That one spin 4, spin 5, spin 6. We have a 7, 8, and a 9. Let's define a lattice constant as that length with a little L. And now let's play the exact same game. We have some original model that exists on this original scale with spins sitting at these vertices. And let's imagine integrating out half of the spins. Let's say this time we integrate out all the odd spins. Well, what will we get back? Okay, we've integrated out S7. There's integrating out S1, S5, S3, like so. There will be new interactions that were mediated by those spins that now couple the remaining odd spins. the links have indeed changed, not as dramatically. Now they've increased by a factor of the square root of 2. And if I was to flip that around, say like so, oh, how is that for fanciness? It looks like a square lattice again. So some of this structure is here. We integrate out half the spins, a sublattice in 2 dimensions. We get back another square lattice, but one you got to kind of tilt your head to notice. So again, we've taken this original square lattice, we've integrated out the odd spin. So for example, if we thought about spin number 5, the fluctuations of spin 5, there in the middle, well, even though 2 and 4 don't directly link up with each other, 2 interacts with 5, 4 interacts with 5, so in effect, 2 interacts with 4. And that spin 5 will then couple 2, 4, spin 6, and spin 8. And when we integrate those spins out, we get a square lattice back. Okay, that's the picture. What about the math? So we have some sum over S5. Let's think about the consequences of S5. We originally have e to the k. S5 interacted with 2, 4, 6, and 8. So I have 2 plus 4 plus 6 plus 8. Those are all of the terms associated with S5. Again, that's a sum I can do. There's only 2 terms in that sum. Evaluating it, I get twice hyperbolic cosine of k S2 plus S4 plus S6 plus S8. And as before, the question is, can we write this as some constant that depends on k? And a new Ising model, in which case we have interactions between S2 and S4. We have interactions here between S2 and S6. We have a 6 and an 8, and a 8 and a 4. Is that possible? All right, well, if we think about that, this is our new lattice. With 2, 4, 6, and 8 sitting on it. Well, if I had a, say, spin, that was spin 4 sitting there pointing up, S2 pointing up, these 2, 6, and 8 pointing down, and an arrangement like this, the total sum S2 plus S4 plus S6 plus S8 is the same, which is what goes into this equation. That's just the sum of those even remaining spins. But if I ask about what that equation has to be equal, product of 2 and 4, 2 and 6, 6 and 8, 8 and 4, those are going to be different. So in fact, there is no way to rewrite this term as something that looks exactly like that term. There's essentially too much redundancy in having just these simple interactions of picking out specifically 2 and 4, 2 and 6, 6 and 8, 8 and 4. Too many different ways that those can be that are degenerate with the sum being one defined number. Moreover, physically, I've drawn this picture a little carelessly. The way that 5 sitting in the center here generates an interaction between 2 and 4 is fundamentally not so different than how it would introduce an interaction between 4 and 6, something I did not put in this drawing. Similarly, 2 and 8, from the perspective of 5, are the same, so there's no reason I shouldn't have an interaction like that. That adding in extra interactions, unfortunately, by itself is not sufficient. That still leaves too many unknowns, not enough independent equations. So in fact, the simplest way to save this transformation is to make the model that we renormalize to more complicated. The effective function E or beta A tilde of the even spins the simplest thing that we can do is to write it as a constant, say log of some f of k, plus something with some interaction k1 times the set of interactions we had before, 2 and 6, 6 and 8, 8 and 4, 4 and 2, plus some interaction, call it K2, S 2 and 8, and 4 and 8. Those were those diagonal interactions. Plus, we need one, turns out we need one more equation, one more unknown to satisfy the numbers of unknown interactions we have, call it some K4. That reminds you, this is all at some zero external field, so the system has to have up-down symmetry. So the simplest symmetry allowed interaction I can generate has to be an even multiple product of spins. So therefore the simplest interaction, in addition to those pair interactions, would be a fourth order interaction that multiplied 2, 4, 6, and 8 with each other. So those are all those terms associated with integrating out spin 5. And I will have the same sets then for all other odd spins. Say a set of terms from S1 plus a set of terms from S3, etc. So again, to write out the model, when we integrate out half of the spins that would have sat at those places, we get a interaction that looks like the original Ising model on a square lattice. In addition, we have interactions across the diagonal and a new four-body interaction that couples all of the spins at the same time. That one we've called K4. We have a K1 and a K2. Okay, so this is the new energy function we're renormalizing to. We still have a whole bunch of unknowns we have to solve. We have an f of k, k1, a k2, and a k4 to solve for. So let's do the same game we had before. We have now 4 unknowns. We need 4 equations. So we have variables that's 2, 4, 6, and 8. We have some hyperbolic cosine k, the sum 2, 4, 6, and 8. That was our partition function, or the result of summing over S5. And now we have our f of k, our term that goes like k1, term that goes like k2, and the term that goes like k4. Well, one possibility is that they're all the same, they're all up, say, in which case I'll have twice hyperbolic cosine of 4k. I'll have an f of k, which is spin insensitive, times an exponential of 2k1 plus 2k2 plus k4. Okay, what about if one of them is spin up and all the rest are spin down? I'll have twice hyperbolic cosine of 2k. I'll have f of k. And now the only remaining term is minus k4. Okay, those are two equations. Need two more. What if two of the spins are down and the rest are up? In that way or in that way. Again, depending on whether or not the spins lie along their diagonal or along the outside of the square, they function differently in that quadrant. So if two are down and two are up, the sum of them is 0. So I have hyperbolic cosine of 0, which is 1 times 2 gives me 2. That's in both those cases. And our mapping function still has a f of k. And in this one, I will get a minus 2k2 plus a k4. And here I will get a minus 2k1 plus 2k2 plus k4. So there are my four equations, four unknowns, big old mess, but one can solve it. And drum roll, if I solve those for k1, I will get 1/4 times the log of hyperbolic cosine of 4k. The solution for k2 is 1/8 log hyperbolic cosine of 4k. k4 is k2 less 1/2 log hyperbolic cosine of 2k. And that constant f of k is equal to twice hyperbolic cosine of 2k to the 1/2 times hyperbolic cosine of 4k to the 1/8. Pretty ugly, but just some algebra after it's set up. Okay, now we only get progress within the renormalization group by iterating this map. So what happens if we try to do this whole thing again? A huge mess. We had these spins, 2, 4, 6, and 8. They interacted directly along their diagonals and through this 4-body term. They're embedded in an infinite lattice. If I try to integrate out some number of those spins, say integrate out spin 2 and 8, I won't be able to independently sum over 2 or 8 anymore. Two and 8 interact directly. I can't carry out that sum over 2 by itself. So in fact, trying to recur this map generates new and new interactions at each level. It's a huge mess. So we can't actually do this in practice. So what can we do? Well, if we didn't have those interactions along the diagonal or that 4-body interaction, then we would have really gotten the same functional form of the Ising model back, which means that we could turn this crank again and again and again. So we could just decide arbitrarily to set K2 and K4 to 0. maybe making some argument that they're not very important. If we did that, however, we would get the 1D result. We would find that lacking those extra interactions, there is no non-trivial fixed point. So indeed, the generation of these additional interactions is fundamentally related to the critical point. So instead of doing that, an alternative would be to still get rid of K4. Maybe it's not so important. And maybe try to build in the diagonal interaction into the non-diagonal interaction. Pictorially, that would look something like this. We have those interactions along the perimeter. We have the interactions along the diagonal. We could imagine that in effect, what that does, the diagonal interactions are like increasing the effective interaction along the perimeter. This is what is known as bond moving and was proposed by Leo Kandanoff and his student at the time, Migdal. What that would mean mathematically is we would take K prime to be the sum of K1 and K2, which is equal to 3/8 log hyperbolic cosine of 4K, which is a pretty subtle difference from what we had in 1D. In 1D, if you go back up, we had that K prime was equal to 1/2 log hyperbolic cosine of 2K. Here we get 3/8 log hyperbolic cosine of 4K. Pretty subtle difference. Do we get anything interesting? Well, what happens if we put K is 0.1 to the right-hand side? That would map to a K prime, which is slightly smaller. One can do that by noting this Taylor expansion for small k, which would just be log of hyperbolic cosine of a small argument times 3/8. That'll essentially give us first order term is, let's see, that gives us for small k, I think it goes like 3k squared. So if I square it, multiply by 3, indeed it gives me 3/100. What about if k is slightly bigger? Let's start it at 0.7. That will map to a k prime. Toss that through Google. Now, a little calculator, if you have it handy, that actually increases k prime. Let's do this a little more carefully. For large k, the map, k prime goes to 3/8 log hyperbolic cosine of 4k. Well, if k is very big, the positive exponent in hyperbolic cosine will dominate. I'll get e to the a log of e to the 4k. That gives me 4k times 3/8. For large k, I expect k prime to go like 3/2 k minus 3/8 3/8 log 2. Indeed, from the denominator of the exponentials, which asymptotically will go like 3/2 k when that constant is irrelevant. So k prime gets bigger than k. For small k, if I Taylor expand 3/8 log hyperbolic cosine of 4k, I get 3k squared. If I square a small number, I get an even smaller number, so k prime gets less than k. Indeed, if I iterate my renormalization group flow in k, if I start small, I get smaller. If I start big, I get bigger, which must mean that there's a critical value in the middle that separates out those flow behaviors. That's a non-trivial fixed point. That's pretty exciting. We've developed a approximate technique that differentiates between 1 and 2 dimensions. It correctly predicts a fixed point non-trivially in 2 dimensions that was not there in 1 dimension. In fact, you can compute numerically where that fixed point is, and it happens that k is about 0.51, which means that there's a prediction for the critical point from RG, which is about close to 2 J over KB. Remember, Onsager's solution was 2.26, and our mean field prediction was 4. So we're doing way better than mean field, and actually pretty good. Pretty good. For something that we, mind you, Onsager's exact solution takes about 40 pages of algebra. We've just sketched this out in 2 pages, and we're getting a pretty quantitative estimate of the critical point. And in fact, as I've alluded to, one can do better. One can make a slightly more quantitative estimate by adding some bells and whistles. What about critical exponents? How about our correlation length exponent, which we know goes like t minus tc to the minus nu. In 2 dimensions, we expect nu to be 1. We predicted in mean field a value of 1/2. We don't really work with temperatures in RG. We work with those coupling constants, but they're simply related. So we expect the correlation length to diverge as k approaches its critical point. So how can we work out what that correlation length is? Well, upon rescaling this spin decimation, we take our correlation length and divide it by the square root of 2. That gives us a new system. If spins are correlated over a length scale c, as I increase the system size, it looks like that correlation length has shrunk because I've gone to a larger scale. The lattice size is increased. Near Tc, we have that k is approximately Kc plus some correction to first order. we expect that K prime is Kc plus some correction, which is not the same correction, but weighted by how K changes with K prime, evaluated at Kc. Again, exactly at Kc, K is equal to K prime. They map to each other. But away, there are corrections that change depending if I'm looking at K or Kc, or K or K prime. This differential we can work out from our map, gives us 3/2 hyperbolic tangent of 4K evaluated at Kc, which we know is 0.51, gives us a number 1.45. So the correlation length in the zoomed out system relative to the original system, since they both go like K minus Kc to the minus nu, we know that that ratio is 1 over the square root of 2, and that's equal to delta K times 1.45 to the minus nu over delta K to the minus nu from these two expressions, taking that Kc over to the left-hand side. Those delta K's drop out, both being to the minus nu, so we can solve for nu, and we get log of square root of 2 divided by log of 1.45, which if you run that through your calculator is 0.94, which is not too bad. It's pretty close to 1, much closer than a half is that we got from mean field. It's perturbatively close. In fact, we could add some bells and whistles, some perturbation theory on top of all this and actually get it exactly right. So this is a very different way of thinking about computing our physical system. The renormalization group works especially well in systems that have self-similarity, in systems that you can write this map down for and iterate it. It required this kind of ad hoc fix, this bond moving that Kandanoff expressed. That's the thing that one could do a little bit better with. It's a little hard to do it on a lattice. Wilson, whose work won the Nobel Prize for the renormalization group, figured out a way to do this by first mapping the system to a continuum. But indeed, you can kind of see how this can generate non-rational exponents. There's nothing here that's solving an algebraic equation to get out observable properties. This is working with a set of flows whose fixed points need not have anything to do with the rational numbers. All right.